Hi everyone, I'm Anthony Usha, Assistant Professor from the Department of Aeronautical Engineering in Gojan School of Business and Technology. From the Unit 4, Aircraft Stability and Structural Theory, we are going to discuss some few important topics. Let's get into Unit wise deeply. Unit 4, Aircraft Stability and Structural Theory. Degree of freedom of aircraft motions, stable, unstable and neutral stability, concept of static stability, Hooke's law, brittle and ductile material, moment of inertia and sections. These are the syllabus which we are going to discuss about here about the aircraft structural and stability. Important topics from the unit of 4 goes like degrees of freedom of aircraft, control surfaces and their effects, stability in aircraft, Hooke's law, moment of inertia. Degree of freedom of aircraft motion. In aircraft stability and structural theory, we begin with the degree of freedom of aircraft motion. There are 6 in total, 3 translational and 3 rotational, which define how an aircraft can move in space. 3 rotational plus 3 translational gives 6 degree of freedoms in aircraft. Aircraft can freely move in space. There are three axes which shown in the slide are x-axis that is longitudinal, y-axis which is lateral and z is vertical. In aviation, an aircraft moves in three main rotational axes which are pitch, roll and yaw. Pitch shown in yellow tilts the nose up or down around the lateral axis and roll in tail rotates the wing up and down around the longitudinal axis. Yaw in blue swings the nose left or right around the vertical axis. Together these motions allows an aircraft to maneuver in three-dimensional space maintaining control and stability in flight. Degree of freedom of aircraft motions. As we shown in the earlier slide, there is two movements that are translational and rotational. Here we are going to see the translational movements in deep. That is surge which is upon the x-axis, the movement is in forward and backward. The next is wave y-axis that is side to side and heave z-axis which is depends on up and down. From the picture we can depict that the x and y and z axis movements very clearly based on its movements. Under aircraft motion, we are going to see rotational movements and its type, which based on its axis. Roll, rotation about x-axis, right wing down is equal to the positive roll. Pitch, rotation about y-axis, nose up, positive pitch. Yeah, rotation about z-axis, nose right and positive yeah. So from the diagram we can show that the axis in y-axis is pitch and in x-axis which shows the roll and in z-axis where we can say the yaw moment is there. Aircraft movement axis and control. For the ease of understand between the two movements that is the translational and rotational, I have differentiate and made an slide for your reference where in the left side I have placed the three types of rotational movements that is yaw, pitch and roll, and in the right side I have placed the three types of translational motions where yaw which is based on the z-axis rotation about the z-axis nose left or nose controlled by the rudder, and whereas in the translational motion we refers to heave which the axis z up and down controlled by lift, whereas in pitch in y-axis, nose up and down, which controlled by elevator. Here in translational motion, we consider it as sway, movement along the y-axis left or right, which is influenced by crosswinds. Here in rotational, we said as roll, which is based on the x-axis side to side, which controlled by ailerons. And here in translational, the movement along x-axis forward or backward, which is controlled by thrust. From this slide, we can easily find the roll movements, yaw movement and pitch movement. In the roll, which uses the ailerons to control, and in yaw, which uses the rudder to control, and in pitch, which uses the elevator to control its movements. And here, based on its axis, the picture depicts the movements. In longitudinal, the roll which acts to ailerons to control. In the vertical, the yaw movement which take place, the rudder to control, and in lateral, the pitch movement which the elevator to control. So from the give images, we can easily identify what is the movements and what is the uh, controlling surfaces which is used to control the flight to deviate its axis. Coordinate system of an aircraft. There is two basic coordinate system. First one is body fixed coordinate system, which moves with the aircraft, which is defined by its aircraft structure, which based on x, y, z axis, that is longitudinal, lateral and vertical. In longitudinal, which is nose to tail, lateral wingtip to wingtip and vertical bottom to top, based on the downward, which is always in positive. And here in earth fixed coordinate system is the coordinates that with respect to the earth. Here the x-axis based on north, y-axis based on earth and z-axis based on down, which is towards the earth center, and which is used for navigating and tracking, whereas in body fixed coordinate system, which is used to describe the orientations, forces and moments. Okay, and from the diagram there is a point 2 which flight in the flight path, that is depicts the flight path, and where the translation motion between earth fixed coordinations to body fixed coordinate system. Coordinate system comparison. In aerospace engineering and flight dynamics, we often describe an aircraft motion using two distinct coordinate systems, that is body fixed and earth fixed reference frames. Let's begin with the body fixed frame. As the name suggests, this coordinate system is attached to and move with an aircraft. The x-axis point forward along the aircraft nose. The y-axis point towards the right wing and the z-axis downward, that is through the belly of the aircraft. This frame is essential for describing the aircraft attitude, such as pitch, roll and yaw, which analyze the force, moments and control inputs from the pilot or autopilot systems. Because this frame rotates and translates with the aircraft, it provides a useful perspective for understanding how the aircraft behave in response to internal changes. On the other hand, the earth fixed frame is stationary and aligned with the Earth's surface. Its x-axis points geographical north and the y-axis points east and the z-axis points downward toward the center of the Earth. So the frame is primarily used for determining the aircraft position, velocity and navigation, such as tracking its location on a map, calculating GPS coordinates or planning a flight path. So the key difference is that the body fixed frame moves with the aircraft and is ideal for internal dynamics, while the Earth fixed frame stays constant and is crucial for external navigation. In practice, both frames are essential. So whether it's navigating across continents or analyzing how control surfaces which affects the flight. Control surfaces. Aircraft control surfaces is basically classified into primary control surface and secondary control surface. Under primary control surface, ailerons, elevators and rudders which comes, and in secondary control surfaces, flaps, slats and spoilers will come. And from these control surfaces, we will control the translational and rotational motions in common. Aircraft control surfaces are essential parts that allow the pilot to control the aircraft orientations during flight. So I have colored the control surfaces which easily understandable. So ailerons, which is located on both wings, that is in red color, which control roll. When one aileron moves up and the other will comes down, it creates a difference in lift which causes the aircraft to tilt sideways for turning. So then elevators, which is in blue, attached to the horizontal stabilizer, controls pitch. Moving the elevator up and down causes the nose to rise and fall, letting the aircraft climb and descend. Rudder. Rudder is in green and which is found on the vertical stabilizer manages yaw. It moves aircraft nose left and right which helps with direction and coordinate turn. And together these three primary control surfaces, aileron, rudder and elevator, work to stabilize and maneuver the aircraft across all three axes of flight. So spoilers, flaps and slats are the secondary control surfaces which used to reduce the drag and also to increase the lift. Aircraft control surface comparison based on location, function, action and its effects. So we are going to compare the primary control surfaces which are aileron, rudder and elevator. So in flight, in an aircraft is controlled using three primary control surfaces as we already know that. First, the aileron located on both wings and control raw. When one aileron moves up and down, there will be a differential lift which causes the left and right motions. We already know that, right? So next, the elevator found on the horizontal stabilizer manages the aircraft pitch moving up and down so that the nose angle allows the aircraft to climb and descend. Finally, the rudder attached to the vertical stabilizer controls yaw. So it moves left and right to steer the aircraft nose direction, helps with the coordinated turns and directional control. So together these control surfaces allows a pilot to maneuver the aircraft smoothly and safely across all three axes of flight. So this slide is for reference and for educational purpose which makes you to easily understand. Secondary control surfaces. So secondary control surfaces means basically classified into four types, that is flaps, slats, spoilers and trim tabs. So in here in flaps, flaps are located on the trailing edge of the wing. When extended, they increase both lift and drag. This allows the aircraft to fly at lower speeds, especially useful during takeoff and landing, which also increase lift and drag. So this is the key point. And next to this, slats. Slats are positioned along the leading edge of the wing. They open up to allow airflow to remain attached to the wing at high angles of attack, improving lift and reduce the risk of stall during slow flight. So which allows to improve the airflow. Spoilers. Spoilers are panels on the top surface of the wing that disrupt airflow when deployed. This reduces lift and increased drag, helping the aircraft to slow down or descend more quickly. They are more commonly used during the landing. So, this is used to disrupt the airflow. Trim tabs. Trim tabs are small adjustable surfaces which is located on the trailing edge of primary control surfaces. They help the pilot to maintain a steady flight path without continuous control input, which reduce fatigue and improve efficiency. So, which is used to reduce the pilot workload. Stability and control. Stability and control are essential aspects of aircraft design. Stability ensures that the aircraft return to its original state after a disturbance, while control allows the pilot to command the aircraft motion. How to ensure aircraft stability and control? Static stability ensures immediate return to original altitude after the disturbance without pilot intervention. Control allow pilot to manipulate aircraft motion predictably. Dynamic stability, which provides stability over time through damped oscillations after the disturbance. Aircraft stability and its type, which is based on static and a dynamic stability. Basically, in static stability, there is stable, unstable, and neutral, as well as in dynamic. So, static stability, which is the initial tendency which occurs after an disturbance. So, dynamic stability is the response over time. So, under static stability, the stable, unstable, and neutral is based on the initial tendency, and here in the dynamic, which based on its stable condition and the oscillational period. So the next, the lateral, longitudinal and directional stability, which based on the axis. These are the axis based stability types. So under the longitudinal stability, which is based on the pitch, static controlled by the CG, which based on the tail plane. So dynamic, phagoid and short period oscillation. So in lateral stability, it is based on roll. Here the static is based on high wing configuration, that is which is achieved through dihedral wings. So and it is dynamic based on the Dutch roll behavior. So it helps the aircraft resist roll disturbances. In directional stability, which based on yaw, where the static provided by vertical fin, dynamic damped yaw oscillations, which also maintains headings in crosswinds. Factors which affects the stability. I have some mentioned some pros and cons based on the facts which we can discuss here. That is the forward CG, center of gravity, proper aerodynamic design, high wing configuration, effective control surfaces. These factors can be mentioned as pros for the affecting stability, and the cons are aft CG, poor aerodynamic design, low wing configurations and ineffective control surfaces may lead to affective the stability in very in poor. Based on aircraft stability and its analysis, I have put this flow chart for your ease of understand. So based on types of stability, basically it is classified into two types, that is static stability and dynamic stability. Under static stability, here comes the positive, neutral and negative static, and in dynamic stability here comes that positive, neutral and negative dynamic stability. So in positive static stability there is three kinds, that is longitudinal, lateral and directional. That is static stability. These are all under positive. And here comes in longitudinal, based on the moments pitching moment, center of gravity, stabilizing surfaces based on the longitudinal static, and in here lateral, which based on the rolling moment, and wing dihedral sweep angle which may occur. So in directional static stability based on z axis, as we know the yaw moment occurs and it may affect the vertical stabilizing controlling surface. So this is the analyzing method I have done for you to make ease of understand the stability. Concept of static stability. Static stability can be defined as the initial response of an aircraft to a disturbance in its flight path. It is basically divided into three types, that is statically positive, neutral and negative. Positive static is an aircraft which is their disturbance which occurs that generates force or moments that tend to restore its original position. For example, if a gust of wind pitches the nose up, a statically stable aircraft will produce a nose down moment to counteract the disturbance. From the first picture, we can show that the center of gravity is based on down and it counteracts the disturbance to retain its original position. So in negative static stability, an aircraft is negatively statically stable if after a disturbance generates force or moments that amplify the deviation from its original positions, where we can see here in the last peak the negative static stability, it deviates from its original position. In this case, the aircraft will continue to diverge from its original attitude without corrective actions. And here comes a neutral static stability, that is in the middle picture. The aircraft has static stability if after a disturbance, if it neither returns to its original position nor diverges further, it remains in the new attitude without generating or restoring or amplifying forces or moments. So it is generating but not amplifying any force or moment. So it is a neutral static stability. So the picture gives the detail about the comparison of static stability and dynamic stability, where the static stability is the initial reaction to disturbance in equilibrium and the dynamic stability is the behavior over time after disturbance in equilibrium. So as we know that static stability is divided into positive, neutral and negative as well as the same in dynamic too. So the positive is tendency to return to its initial position. So neutral is to remain in new position and the negative to tendency to continue moving from the initial position. So in dynamic, whereas the case somewhat differ, right? So tendency to return to its initial position, tendency to remain in new position and also the negative. So tendency to continue moving from the initial positions. But it is over time after the disturbance in equilibrium. That is a small difference here. Axis of an airplane. This diagram shows the three principal motion of an airplane, that is pitching, rolling and yawing, each around a different axis, that is lateral, longitudinal and vertical. So pitching occurs around the lateral axis which runs wingtip to wingtip. When the elevator on the tail moves, it changes the aircraft nose angle up and down. That this is what controls climb or descent. Rolling happens about the longitudinal axis which runs from the nose to the tail. This motion is controlled by the ailerons on the wings, allowing the aircraft to tilt and bank during the turns. Lastly, yawing takes place around the vertical axis which run top to bottom through the aircraft. The rudder controls the motion steering the nose left or right. These three axes of motions are fundamental to how pilots maneuver aircraft in three-dimensional space. Hooke's law. Hooke's law is valid only up to the elastic limit. The deformation of aircraft material is directly proportional to the applied stress. That is, sigma is equal to the product of E and eta, that is Young's modulus and strain. Hooke's law, which is very critical applications in aircraft wing bending. Wings flex under aerodynamic loads but must return to their original position or shape after landing. So Hooke's law helps to predict safe deformation limits. So under the landing gear compression during landing, the strut compress and return elasticity. So behaving according to Hooke's law. Stress analysis. Engineer use it in FEA, that is the finite element analysis, to ensure that aircraft structures remain in the elastic reversible region during the operation to avoid aircraft design for safety. Hooke's law within the elastic limit. So it formed the basis for categorizing the materials based on how they react to the mechanical loads. And let's look at the main categories, right? So brittle materials, where the fractures occur suddenly with a little plastic deformations. In plastic materials which undergoes the permanent deformation even after elastic limit. So viscoelastic materials which deform slowly and recovers gradually over time. So the ductile materials which exhibits significant plastic deformation before breaking. The elastic materials which returns to original shape after load removal. So based on the material type which obeys the Hooke's law, if it is elastic means it returns to its original form. So that are steel, aircraft alloys. If it is not means it may undergo the permanent deformation, that is soft copper lead. So when it is the material is brittle means it can lead to sudden break, which are glass, ceramics. So if it is not, ductile may occur, and the ductile may classified into large plastic deformation and viscoelastic. So if it is large plastic deformation, the materials may aluminium, mild steel. If the viscoelastic occurs, it depends on time and behavior and slowly recover. The materials are rubber and polymers. Stress strain curve. For brittle material, the stress strain curve shows a steep linear rise until the fracture with little to no plastic deformation occurs. The area under the curve is relatively small, indicating low energy absorption before failure. For ductile material, the stress strain curve consists of an initial linear elastic region followed by a yield point and a significant plastic deformation region before the final fracture occurs. The area under the curve is large, indicating high energy absorption. Moment of inertia. Moment of inertia is also called the second moment of area, which is the measure of how a body's mass or area is distributed relative to an axis. So it is plays an crucial role in mechanics, especially in rotational motion and structural engineering. So moment of inertia is the resistance of a body to change in its rotational motion about an axis. For a point mass at distance from x-axis, I is equal to mr square. So I is moment of inertia, m is mass and r is the distance. The moment of inertia is a key concept in aircraft dynamics. It measures how resistant an aircraft is to change its rotational motion around an axis. In simple terms, it tells us how hard it is to pitch, roll, or yaw the aircraft. In aircraft design, the moment of inertia depends on how mass is distributed about the aircraft's three principal axes, that is, the longitudinal, lateral, and directional, which also denoted as I-axis, IYY, and IZZ, about roll, pitch, yaw, and that are the rotational type of its axis. So, which is in the diagram, it shows that the axis and rotational moments. So I have shown some few examples for moment of inertia and how to manage the mass. So in cargo aircraft, stability through mass management. So how to ensure the stability in cargo aircraft? To ensure the stability in cargo aircraft, three key steps must be followed. First, calculate the inertia to accurately understand how mass distributions affects the aircraft behavior. Secondly, load cargo symmetric to prevent unwanted movements and keep handling predictable. So finally, use advanced software to perform precise calculations and assist the loadmasters in planning the safe and balanced flights. So these are the key points where to get the stability in aircraft. Again, the same example, the fighter jet. So agility through low inertia. The factors which affects the agility to low inertia in fighter jets or low moment of inertia, compact components, design strategy, mass concentrations. These are the factors which needs to be balanced and it should be considered unstability condition and the flight jet. So for to get the agility through low inertia. Thanks for watching.